So first, I want to thank the organizers for making this event possible and for giving me the opportunity to present my work. So I'm going to present some recent work with Lucas Pio-Vivien and Nicolas Flammarion on the dynamics of gradient flow for ReLU networks. So there is still a lot of mystery on the theoretical side of what happens when we do train two-layer ReLU neural networks with gradient descent. So among the main questions, we have the following one. So do they converge to zero training loss? Do we have some implicit or simplicity bias that might help in good generalization properties? And what is the role played by the initialization? So for these questions, we only have partial answers, either assuming large initialization, classification, or infinite width networks. So in this presentation, I'm going to assume neither of these cases. And we are going to present a complete answer and description of the training dynamics in the case of orthogonal data for small initialization. Oops, sorry. OK, so there's a small problem. So here's the setting we consider. So we have n data points given by the features xk and the labels yk. And we aim at minimizing the square loss over the parameters theta. So here, theta parameterizes two-layer ReLU networks given by the inner layer weights W and the outer layer weights A. And so as I said, so here we consider a ReLU activation, so the max between x and 0 for the function sigma. And I am going to assume in the complete talk, in the whole talk, that the inputs are orthonormal, meaning that the scalar product between two data points is 0. So being the data points being of norm 1 is not really necessary just for simplicity of exposition. But this is a key assumption that will help us to completely describe everything and derive nice analysis on the theoretical side. And so we're going to study gradient flow, which can be seen as a continuous approximation of gradient descent when the learning rate goes to 0. So this is much easier to analyze, and which is why we analyze it in this presentation. So now let's talk about the initialization. So as I said, the initialization will play a key role in this work. So we consider an initialization where we initialize each neuron inner layer weight according to some Gaussian distribution, so they are RAID, and with a scale lambda. So this lambda term is the key and corresponds to the scale of initialization. So as I said, I'm going to study the case of small initialization, so lambda would be very close to 0 afterwards. And we consider a balanced initialization, meaning that the value of the outer layer weights are equal to the norm of the inner layer weights up to a sign that is chosen randomly at the initialization. So from there, we have a very well-known property that for gradient flow, we will keep the balancedness all along the training trajectory, and that the weights won't reach 0 in finite time. So this is really crucial in the analysis that will follow. And we will also need some key sets that corresponds to S plus and S minus. So S plus is just the set of neurons which at initialization have a positive outer layer weight and whose inner layer weight is positively correlated to all the data points whose labels is positive. And so we have the corresponding set S minus, for which the outer weights are negative and which are positively correlated with negative labels. And I am going to consider this key assumption about the initialization that both sets S plus and S minus are non-empty. So for this assumption to hold with high probability, when we have, for example, omnidirectional initialization as this Gaussian initialization, we need a large number of neurons. Actually, we need of the order 2 power n neurons to hold it with high probability. But I'm going to discuss this assumption a bit more later. So here is the main result that we have. We have that if the scale of initialization is small enough, then the gradient flow will converge to some interpolator theta star lambda, so it does depend on lambda. But when lambda also goes to 0, then this final interpolator will converge to some interpolator theta star that is among the set of the minimal norm interpolator. So here we have two different results for small initialization. The first one saying that the training loss will converge to 0, and the second one saying that we have an implicit bias towards minimal norm interpolator. So this implicit bias towards minimal norm interpolator is kind of classical in the case of linear regression, for example, or also linear diagonal networks. And we conjecture it also holds in the general case of two-layer nonlinear networks, at least for ReLU activations. And so many other insights can be differed from the proof. In particular, we can describe completely the trajectory, so I'm going to discuss about it a bit more. So first, thanks to the orthogonal assumption, we are able to exactly express what are the minimal norm interpolators for this problem. And in particular, all the minimal norm interpolators correspond to this estimated function, which can be seen as just a two neurons two-layer neural network. So we have a first neuron corresponding to ND+, which helps at fitting all the positive labels, and a second neuron, which is minus ND-, which helps in fitting all the negative labels. So this is a very simple estimated function in the end, and it is very sparse in the number of neurons that are needed to represent this function. So as I said, we are also able to characterize precisely the training dynamics. So this dynamics is divided into several phases that I'm going to detail further. But for now, just remember that during this training dynamics, the trajectory goes to an intermediate saddle point. And so this is something that has been observed in more general neural networks training and also conjectured in general. And so this intermediate saddle point actually corresponds to the point where only one of the two neurons between D+ and D- has been learned by the network, but the other one remains to be learned. So now about the implicit bias. As I told you, we have some bias towards minimal norm interpolator in terms of L2 norm of the parameters. But we can actually show that this leads directly to some minimality in terms of function norm among the interpolating functions. Sorry. So this norm function is actually known as the F1 norm, and for this norm we know that we can derive good generalization guarantees. So I'm not going to detail about that in this talk, but so this means that thanks to this implicit bias, we might have a very good generalization of our networks. So now about the number of neurons. As I told you, we need a number of neurons that is exponential in the number of data points to have our assumption to hold with high probability. So this is a classical overparametrization assumption, but actually this assumption is only necessary to have convergence towards minimal norm interpolator. So if we have a smaller number of neurons, we will still have convergence towards the training zero loss, and we will have some weaker form of bias, meaning that we will still have a small number of neurons used to represent the final estimated functions, but this number of neurons will be larger than 2. And so it is not minimal in terms of norm. Okay, so now I've given you all the different insights that can be taken from the proof and the theorem. Now I'm going to describe to you exactly the training dynamics, because we are also able to describe it perfectly in the orthogonal case. So now, for this figure, we consider orthogonal data for dimension 2. So the first dimension just corresponds to the x-axis that you see here. And the second one is a one coordinate for all the points, just to take into account the bias term that we use in the inner layer. And so here, each green dot corresponds to a data point. The green line is the estimated function by our neural network. And each blue star represents one single neuron in the hidden layer. So its x-axis corresponds to the king position of its associated ReLU, and its y-axis corresponds to the weight of the outer layer of this neuron, which is, I recall, equal up to some sign to the norm of the neuron of the hidden layer. So let's see what happens during the training dynamic in that case. So here I'm going to show you the complete dynamics, and then I'm going to divide it into several different phases and describe it more precisely. Yeah, so you see that at the end, we reached convergence towards training zero loss, and our function can be really represented as a two neurons neural network. So here we clearly see that we have two neurons represented by the two columns of blue stars. So actually what we had first was the early alignment phase, in which all the neurons move tangentially, so they move in direction towards some key directions, but they do not move in terms of norm, and their norm remain close to 0. And so you see that at the end of this phase, you will have only 2 clusters of neurons, so one which is aligned actually with D+, and one which is aligned with D-. So mathematically, this is what happens in this phase. So if we define bar W, the normalized weight vector of each neuron, or you can just see it as a direction of each neuron, we have the following equations for both the direction and the norm of the neurons. And so you can see that for the first one, it scales in big O1, and so it will evolve in time big O1, while the second equation about the norm, so the second differential equation, scales with the norm of your neuron, which I recall is very small, so it's lambda at the initialization, and because of that, this equation will only evolve in a time that is logarithmic with 1 over lambda. And so we can show the following lemma that for some time that is very small with respect to a logarithm of 1 over lambda, then the alignment will have occurred. So the directions will have aligned either with D+ or D-, and all the neurons will have stayed small in norm, because for the second ODE, nothing will have really happened in this small time. Okay, so now we have our neurons aligned towards key directions, so what happens now? So we have the second phase, where the neurons will grow in norm only, so for example, only the neurons that are aligned with D+ will grow in norm until fitting all the positive labels. And in the same time, all the other neurons remain the same. So in terms of quantitative results, what we have is that all the neurons in S+ and S- will stay aligned with D+ and D- as they were at the end of the first phase. Also, at the end of the second phase, so for some time that we define here, all the neurons in S+ will have grown in norm significantly, and all the other neurons will have stayed small in norm. So to describe this, actually, what we show is that for the function U+ defined as the sum of the squared weights norms, we can show the following approximate differential equation. And from this equation, we can say directly that U+ will grow at an exponential speed towards n norm of D+, and when it has reached n norm of D+, this is when all the positive labels are perfectly fitted. So after the second phase, we have a third phase, which is actually the same, but about the other group of neurons. So the other group of neurons will grow in norm until fitting all the negative labels here. And meanwhile, all the other neurons stay idle. So this is a very similar result that we have for this phase, so I'm not going to detail it. And so after this third phase, what we have is that for some time T3, we are very, very close to some interpolator, and that is almost minimal norm. But nothing guarantees us that it can largely deviate from here until infinity. Well, actually, something does tell us. So using a local Polyakloyevich condition, we can say that the trajectory won't significantly move from the end of phase 3. And so thanks to that, we will converge to some interpolator at infinity that is close to the point that we reach at the end of the third phase. OK, so maybe you've noticed it, but at some point we reach some intermediate saddle point. So the trajectory, as you can see on this plot, goes through 2 saddle points. So the first one given just by the initialization, which is 0. So this is kind of trivial. But the more interesting point is that during the middle of the training, it also goes to a saddle point. And actually, this saddle point exactly corresponds to when to the end of phase 2 until the middle of phase 3. Because at the end of phase 2, so as I said, we've fitted all the positive labels, but it remains to fit all the negative labels. And this is only reached, so we only leave the saddle point when the norm of the second cluster of neurons starts to be significant. And so to summarize the dynamics, as I said, we have the different phases. So the first one, which is the early alignment. Then we have the second phase where we either fit the positive or negative labels. Then we have the third phase where we either fit the negative or positive labels depending on the previous one. And then we have just a final convergence phase that says that we don't move a lot from the end of the third phase. OK, so let's move now to more general cases, because, OK, we're able to describe perfectly what happens in the orthogonal case, but is it significant, and can we derive something from it for the more general cases? So first, let's consider the same two-dimensional example, but with more than 2 data. So then we have no more orthogonality between the data points. And so this is what happened. Actually, we observe a similar kind of behavior, where we have first an early alignment phase. Actually, this phase, we might be able to show it in the more general case. And then we have some convergence towards some very simple function that fits all the data. So we believe that this kind of results actually can be extended to more general setups. But it is very hard to show because actually, if you noticed it, so I'm going to show it again. What happens is that at some point, your neurons will simultaneously grow in norm and change their direction. And this is very hard to describe theoretically in details. And so this is why it's very hard to describe the fully general case for this kind of setting. So here you will see here that we have growth in norm and change of direction at the same time. OK, so I talked a bit about the role of initialization earlier, but I didn't really develop about it. So I said that we considered small initializations because in that case, you have what we call feature learning. And so what happens instead in the case of large initializations? So in the regime of large initialization, we know that we are in what we call the lazy regime, and then the neurons won't move significantly from their starting point. And because of that, so we will be able to converge to zero training loss much faster, but in the end, the interpolated function won't be that simple as it was for the small initialization regime. And so this is why, in practice, you don't really want to be in that regime either. So I guess that in reality, you want to be between both regimes for sure. And so let's now consider another general case. So what happens is if our data is not orthogonal, but almost orthogonal. So this is what would happen, for example, if you consider very high dimensional data, and that the number of data points is smaller than the dimension, and that it is drawn randomly in your space. So in that case, we will observe kind of similar behaviors. First, we will see that in the training loss, you will still observe some saddle point in the middle of the trajectory. And if you look at the projection of your dimension, two-dimensional projection of your hidden layer weights onto the principal components of the representation, you will still observe some early alignment phase where they align towards two main directions, and then you will have this growth in norm of these clusters. But of course, here you do not have clearly two distinct clusters because you are not in the exact orthogonal case, but only in the almost orthogonal case. Yeah, so that's it for me. So in the end, we were able to derive very nice insights and some phenomena in the case of orthogonal data. Some of them were conjectured already for more general setups. And we hope that it can lead us to describe more general cases in the future. So thanks. And if you want to know more about the paper or the code, you can just check it on my website.
Questions for Etienne? Mm-hmm.
Hi, nice result. Can you elaborate more on the exponential relation between the number of neurons and training points?
Yeah.
Where does it come from? Do you?
So why do we need that number of neurons?
To reach the why do you need that number to reach the minimal norm?
Why do I need it?
Yes.
Because actually, okay, so let's go back to the beginning. Sorry, it's a bit slow. Okay, so here, S plus, so let's just focus on S plus, for example. S plus just says that at the initialization, you have at least one neuron in some cone or in terms of direction. And so this cone actually is only given by your sign towards key directions. So you can actually directly compute what is the probability of being in that cone for a single neuron at initialization. Right. And it will mostly grow in a 2 power minus n over 2 or something like that. And so that's how you can say that your required number of neurons to have this assumption in general is 2 power n. But actually, we believe that this is the orthogonal case for this kind of assumption is actually the worst case because you have some, let's say that you can't really cross some barriers for the gradient flow in the training process in the case of orthogonal data, while you can in more general cases. And so I believe that because of that, if you had some equivalent assumption on the general case, it would be easier to actually have it. So as I said, if you have only, for example, a polynomial number of neurons with respect to your number of data points, in that case, you will still have some weaker bias, meaning that in the end, you won't have only two neurons in your final represented functions, but maybe 4 or 5 or something like that. But still, maybe a small one, if you are if your polynomial in n, but large enough.
Thank you.
Thank you for the question. Other questions for Etienne? There's one more question from here.
Thank you. I was curious at some point, it was a bit fast, I'm not sure I got everything, but at some point you said about this equivalence to a neural network with 2 hidden neurons.
Yeah.
So are you actually learning only what a 2 hidden neuron network could learn, or are you learning more? Or if you ran gradient descent on that one, would it give you the same performance? We were not really talking about test error.
Yes,
really.
So the final represented function that we learn is the same as this one, so as the 2 neurons. But in the end, the number of neurons that will be non-zero is much more, because we have many, many neurons towards the same direction. So it's like the neuron splitting Bertin was talking about yesterday. You could say that these 2 neurons, so for 1 neuron, you split it into many of them that represent the same directions, but in the end, your represented function is just equivalent to 2 neurons.
And if I learn directly with just 2 neurons, would I be able to learn the same thing?
No, because in that case, you will need to have a perfect initialization. So if you have the condition, this assumption, yes, you would. But you would be very lucky to have it with only 2 neurons.
Okay. And I'm kind of thinking about the generalization, because the last example you showed was with 6 hidden neurons, the teacher.
Yeah.
And then you learn a function that can be represented with 2 hidden neurons. So it seems that it cannot represent the function you actually started with.
No, actually it's not only 2 neurons a represented function. So actually here we only projected on 2 directions to be able to visualize something, because we can't visualize anything in a dimension 150. But even there, you can see that actually you have more than 2 directions. Like, you see, you have a third one and almost a fourth one that already appears. And I guess that if you look at, for example, the third and fourth components in your PCA, then you will see at least 6 directions.
Sorry, I'm confused, because then the previous claim that I was asking about, that you learn a function that can be represented with only 2 neurons, so here it is not true? Or?
Yeah, because the previous claim was in the case of orthogonal data. Here the data is not orthogonal. It's almost orthogonal, but it isn't.
And if I made it orthogonal, then I could not learn these 6 neurons.
If you make it orthogonal, then you should only learn 2 neurons. And not the truth, because you do not have enough information in your data set. Actually, you will learn something that is even simpler than the teacher.
Right. So that seems like a rather weak learner.
Yeah, but because I think it's because it's the best aim that you can do based on the data set that you are given.
Thank you for the question, Lenka. And there's one more question.
Thanks for the presentation. I would like to ask about what you mentioned for the general case. So you mentioned that there's difficulty quantifying the behavior there because there's rotation and amplitude increase at the same time.
Yeah.
I think for orthogonal case, rotation also coexists with magnitude change. I wonder why is that easy to control in orthogonal case?
Because what happens really in the orthogonal case is that the neurons that are aligned, for example, with D+, and the ones that are aligned with D-,
yes,
because of the orthogonality, they won't interact with each other. While in the general case, you will have some interactions between the different clusters of neurons.
Mm-hmm.
And so this is what will mess up everything in the analysis.
Okay, but if you look into the formula of the D vector, either it is D+ or D-, it is the input weighted by the error, right?
Yeah.
And okay, and So this d vector is the driving force, is the attracting angle of all the weights,
Yeah,
right?
and they are orthogonal altogether.
Yes, yes. But for example, let's look at d plus now.
Yeah.
So all the labels there, are you sure that all the input vectors weighted by the error at any training point, they won't rotate? So because it's a sum of vectors, how do you know that this attracting angle do not change in the course of training?
Because at the beginning they have zero norm almost.
Yes.
And so your estimated function is almost zero.
Yes.
And so even if it moves in terms of angle,
yes, yes,
your estimated function won't change. It will still be zero.
Okay, but so after they have considerable magnitude, it may rotate, right?
Yes, but it doesn't because of what I told you. Because once they have grown in magnitude, they are already aligned towards d plus and d minus, and then they don't mess up with each other. But it's very technical to show.
Okay, I see. So you mean at that point the error will be somehow negligible. So the error term, the weight of the input sum, the input vector will be some sort of fixed, right?
Yeah, you can say that.
Okay, I see. Thank you.
Thanks.